if I don't start the recording, so let's do that. Okay, we got it. Did I forget anything? You guys can see this screen, Zoomers can see this screen, everybody can hear me? Okay,
Yes.
do you want to say something? Folks in the back, say hello.
Hi guys.
All right, can you guys hear the students? Okay, loud enough? All right. If someone asks a question and you can't hear the question, please let me know and I'll do my best to repeat it. What I have is a professional grade microphone that's supposed to be capturing both directions at the same time. So ideally we'll all be able to hear each other, but I haven't tested it out very much, so we'll find out. All right, so let's see, announcements. This class already did homework, so that's good. I did spend the morning recording videos that may be of interest to anyone who is new to SAS or Stata or R. So I have, let's see here, right here, I moved it. So that, my other class, which I will open in a new link here. So this class is orange. The other class that meets after this is blue. I keep everything color-coded so that when I know what I'm looking at, since all of my pages and things look the same. But I just posted on their class at 2-7, there's a handout, how to get started with the University of Iowa Virtual Desktop. I made a video demonstrating the handout, and this morning I also made videos for how to get started with SAS if you've never used it before, how to get started with Stata if you've never used it before, and then I ran out of time before recording the R video. Because I decided since I was showing up in person, I actually had to wash my hair instead of just using dry shampoo and hoping for the best. You know, I'd rather bring my A game to be in person, right? So you guys get clean hair.
Oh my god.
I know, it's very important, but I gotta put on my best face forward, as they say. So R is forthcoming. Although I will tell everybody that do not try to use R inside the virtual desktop. It is hella slow. So just install R on your own devices. You can do it if you have a Mac or Windows. I'm not sure about Chromebooks or sort of like not quite computers or iPads or things, but if you have a regular laptop or computer, you should be able to install R. And if you haven't done so, start with R and then install RStudio. And the way that you will call R is through RStudio. So I will demonstrate that in videos if you haven't had a chance to do that. So let's see, that's that. First formative assessment is going to be due on Monday night. It's worth 2 points if you give it a shot. We have not covered everything that's in it yet, but by the end of today we will have. So at some point between the end of class today and Monday night, if you could give those questions a try. The fourth question merits some explanation if you're new to me. The fourth question on your first formative assessment asks for this semester's theme song for yourself. So a theme song to me is like if you played a professional sport and you were joining the game or joining the match, right? What is playing on the loudspeakers as they announce your arrival? Like that's your theme song. So I'd like to get to know each of you a little bit better. I change out my theme song every semester. I've got one locked and loaded, but I want to hear yours. So the fourth question is asking about that. If you would be willing to share it, if you could put a YouTube link in your answer, I will put together a playlist of all of your theme songs for the class, so we can all sort of get to know each other that way. I don't have whose is whose on the playlist, it'll be a surprise. But just for something a little bit fun for me and maybe a little bit fun for you. So. Zoomers, am I frozen? No, we're good? Okay. And I'm not frozen clearly, I'm in person, so we're good here. There's that too. Good, thank you for the thumbs. All right, any questions, comments, logistical issues, anything I should know about from anybody? No? Okay. We're good to go?
Yeah.
Good to jump back in? All right, what are we good to do? Let's find that out. We've got lecture 1, that's what we were working on. So getting reacquainted with just regular old linear models, which should be on familiar terms with everybody, but also talking about how to code up categorical predictors in different ways to get pieces of information that are useful, as well as how to decompose interaction terms. So that's the big one, because most of our examples are going to have an interaction of some kind, because interactions are almost always used to address research questions. Research questions are, there's really two kinds that you will come across, like, is there an effect of a predictor after controlling for some other stuff, or is the effect of the predictor the same for all different kinds of people? Like, those are the two basic kinds of research questions that you come across, and each of those is answerable in linear models with multiple predictors included and linear models with interaction terms included in particular. So, as a bonus, I put this in my email, but just in case you haven't had a chance to do so, there is one more slide added to this lecture based on Vladimir's question last time about effect coding. So this is an example of why it is useful to attend class even if the lecture is available online, because these lectures are not set in stone. So if I come up with something that you guys have more questions about and I can help clarify by adding things or changing things, I will. And for those of you who are listening at home because you have conflicts with this or because you're sick or whatever else, shoot me emails if you have questions, and I will try to adjust as I can. I teach a lot of different classes, and so I have a lot of different materials I can pull from. Just as an example, in our first unit with binary outcomes, because I've been getting so many questions about IRT, I'm going to flip a couple slides in there from my IRT unit in SEM so that I can actually talk about how the things are related. So that is forthcoming. But I added this one slide to the end of the lecture based on the questions that I had gotten. So, all right, we were here-ish, talking about centering predictors, slide 7 of lecture 1. And now I'm going to attempt to drink my Mountain Dew from inside my mask with a little straw. There we go. Victory is mine. For the record, we're not supposed to have food or drinks in here, but I don't care. So just don't spill anything, all right? If you have drinks that have lids, that's good otherwise. But you're welcome to bring your lunch or your snacks or whatever gets you through the day. And of course, you know, for folks at home, you have whatever rules apply to your couch, right? Like at my house, we don't eat on the couch because I hate crumbs. And the dining table is like 4 steps from the couch. But, you know, you do you in your own apartments and houses. So, anywho. We're talking about scaling predictors. So, even though it doesn't always matter, I want you to get in the habit of thinking about what a predictor represents and how you can make 0 a meaningful value. So we talked about that last time. It always matters in terms of interpreting the fixed intercept in a linear model solution. It will sometimes matter if you have interaction terms, and it always matters if you have random slopes in more advanced models. So this process of changing a quantitative variable so that 0 means something is referred to as centering, and it's constant centering if you know other kinds, meaning that you subtract a constant. It is often called grand mean centering as well, because a grand mean is commonly used as a constant, but it doesn't have to be. So for example, I think I have a slide on this. I had a slide on this. Let me go back. I had a picture. This picture, this is the one I was thinking of. In this picture that we did last time, this is slide 3, I centered years of education at 12. So I happen to know that the mean of education in this particular data set that I was working with is 13.44 years of education. I guarantee no one wrote that down as their answer, that they have 13.44 years of education. So even though the grand mean would make a nice 0 point in certain contexts, if you have a variable where the numbers actually have meaning outside that variable, pick a representative value that's somewhere near the middle. Alternatively, if you have something like a Likert scale, now I don't remember what the correct way of saying it is, and you have like Likert, thank you.
Likert.
See, I've corrected myself so many times that now I can't remember which it is. So, Likert, whatever. If you have like a 1 to 5 ordinal scale, you could pick 3, for instance. Somebody who's sort of midway on the scale, you could pick 1. Somebody who's at the bottom of the scale, and that way when you talk about the change in y for a 1 unit change in x, you can think about moving from the bottom of the scale to the top. So point being, what number it is up to you, so long as the number means something. All right, back to this then. For categorical predictors then. Same principle applies, but there's many different ways that you can code categorical predictors. I put a reference on your reading list that was an article recently published that I thought was a really good treatment of this and how to think, like, basically what do you want to represent about your categories? There's not necessarily a right or wrong way to do it, but there are different ways that are more or less useful. And so in this class, we're going to code up our categorical predictors manually. And I will show you lots of examples of how to do that.
Lisa,
Hit me. Question from the audience.
can you give us the name of the paper?
Can I give you the name of the paper? Yes. It will take me one moment to pull up a web page that has our syllabus on it. My little laptop is churning.
I can give you the names we have for this week. We have Agresti, Hoffman, Enders, and Finas and Goldstein.
All right. Where is it then? Maybe I didn't put it on this class. I should have. If I didn't put it on this class, it's on the other class, and I need to move it over. Nope. Okay, it's on the other class. It is. I will put this on, update the reading lists and such. 67, 62, 43. There we go. It is this one. Authors are Joffrey and Fries, 2021, Reconsidering the Reference Category. So that was the one I was mentioning. If I didn't put it on your reading list, then I meant to. So I will make that adjustment. I thought they did a nice job of describing this stuff. Point being, when we have categorical predictors, in most cases you want to be able to represent the potential mean of each of your categories separately. The question is, how do your model parameters rearrange themselves to do so? So if I have 4 possible categories, I know that at a minimum I need 4 fixed effects. I need an intercept and I need 3 slopes. If I have 5 categories, I need 4 slopes. As long as I have as many slopes plus an intercept as I have categories, each of those category means can be perfectly recreated by the model. However, not by the fixed effects alone. The fixed effects are only going to get us part of the story. So one of the things that I want to show you is how to ask for linear combinations of fixed effects that fill in the missing pieces. And I'll show you what I mean in just a second. So the coding scheme that I greatly favor is dummy coding, in which there's zeros or ones only. Okay, question?
No.
No? You're good? Just stretching?
I'm good, I'm just stretching.
Okay, I'm stretching too. There we go. Any questions from the Zoomers yet? Okay, I'm watching the chat window, so I'm trying to keep everybody at the same time here. So dummy coding, here's one coding scheme. I didn't know this had a name, but in the textbook that I found for the other class, they called this indicator coding, so let's just go with that. When people use the phrase dummy coding, this is usually what they're talking about. So in this case, one of the groups is designated as a 0 for all of the predictors. That means they're the reference group. So in this little coding table, I have 3 columns because I have 3 groups. The first column is not something that you normally think about, even though it's in the model for you. It's added by default, and that's the fixed intercept. So if I were to represent a variable that multiplies the beta 0 fixed intercept, that variable would just be a column of 1s, meaning that everybody starts out with the beta 0 as the basis for their predicted outcome. The question is, what else do we add to it? So everybody gets an intercept. In this coding scheme, I have group A here that is designated as the reference. And I know that because by definition, the model intercept is when all the predictors are 0. So if I give them 0 values on those predictor variables, that makes group A my reference group. I set that up. If I wanted group C to be my reference group instead, I'd give them the zeros. Then when each of these 2 predictors, I've labeled them A versus B and A versus C, when each of these is included together at the same time, then they mean the following things. We have the difference between A and B, so it's how B differs from A as the reference. So when I say A versus B, you'll see that notation from me a lot this semester. I mean the reference is first, and then the comparison alternative group is second. So the parameter would be how B differs from A, which matters for sign. So if this predictor, A versus B, had a positive slope, that would mean that the B group is higher than the A group on average. If it had a negative slope, the B group is lower. Then this one kicks in to differentiate A versus C. And so then this will give us A versus C as a slope in the same direction, how C differs from A. But there's one more comparison that's not going to be represented here. What's missing?
B and C.
B and C. Now how do I get that?
Comparing the means of the groups, B and C.
Yeah. What if I wanted a significance test for B versus C? What are my choices? Zoomers have it. LinCom. LinCom is the stata command. Estimate is the SAS command. Test is the SPSS command. GLHT is the R command. Model constraint with new is the M+ command. And that's all the software I know. But point being, you can do this in any program. You can ask the program to make a linear combination of fixed effects. So that's how we get the missing contrast as well as the model implied means and their standard errors and whatever significance test we want for that. Yes, sir. Question?
Last semester in design of experiments, we used some packages and functions to estimate the mean differences. For example, Tukey or Bonferroni. It is the same. The differences that we get with those packages and functions are the same thing if we compare the means directly using the things that you are talking about?
The difference would be whether or not you ask for an adjusted p-value based on the comparisons that you've made or whether you don't. So what I tend to prefer to show is how to actually get these values, I would say manually, but in the program, rather than relying on a package, because I want you to understand what the package is actually doing behind the scenes so that you can get anything you want, not just what the package gives you.
Okay.
In R, there are several places where I had to override some kind of adjusted p-value rule that it was implementing for multiple comparisons.
Yeah.
My own perspective is that that's not something that I worry about.
Okay.
I just don't. I feel like the way that multiple comparisons are treated is unfairly different than the way that you would consider, say, a regression model with 20 predictors versus 20 post hoc comparisons. Like, it's the same problem, right? If you do a whole bunch of tests, some are going to be significant by chance. So if you want to correct for that, that's fine, but that's beside the point, I think, in terms of what the point that I'm trying to say is that even though there's 3 parameters here, those 3 parameters give us 1 mean and 2 differences. What we don't know yet directly are the other 2 means and the other difference, but we can ask the model to give it to us from the same model. And that's one of the things I want to show. Okay, other questions? Alrighty. Here's another strategy. So we had a question about whether or not it's okay to treat an ordinal variable as interval. I think, Nathan, this might have been your question like last week. This one's for you and everybody else, because I think this is a useful thing that not many people have come across. So this is what is called by that textbook sequential coding. And this is useful for explicitly testing the pairwise differences between adjacent categories of an ordinal variable. So under this coding scheme, I have the first category as the reference. So let's say that I have a self-reported happiness variable, and it's on a 1 to 5 scale, and each of these numbers has some verbal label associated with it, whatever, doesn't matter for our purposes. Here's my intercept, here are my 4 slopes. So I'm still following the same rule that I've got 5 parameters that are going to perfectly recreate my 5 means. Here's my intercept, it's going to be for the group that's coded 0 across, that's happy equals 1. The first slope, H1 versus H2, is going to capture the difference between 1 and 2. The second slope captures 2 versus 3, 3 versus 4, and 4 versus 5. So each of the parameters inches you up on the ordinal scale 1 unit. So for ordinal variables, I think this is more useful than an indicator approach that would reset you back to the 0 point at each time. The difference is right here. So this little red square, that's the difference. It's whether or not the coding scheme represents that category or higher, or just that category. Another way of phrasing the same model would be a piecewise model. That's actually going to be, I think, the next slide on here. So then this type of coding scheme would allow you to test whether or not each of these sequential differences is the same. So think about it. If you're inching along the x-axis, right, and you've got 1 versus 2, and then 2 versus 3, and 3 versus 4, and 4 versus 5, if all of those differences are the same, what do you got? A line. So the end result of these differences being equal is a linear slope through this ordinal variable that pretends it's integral. That's a testable hypothesis. So you can decide based on the data whether it's a reasonable thing to draw a line through it based on whether each of these sequential differences is of equal magnitude. Either way though, whatever is not directly provided by the model is still in there. You just got to know how to ask for it as a linear combination of the fixed effects that you have. So that's what I wanted to show you next using this group coding scheme. Because your first assignment, which is not yet available but which is coming soon, is going to have a 4-group story to it. And I'll be asking you to use this indicator coding because it's a nominal group variable. Okay, how are we doing? With me so far? Any of that you want to hear again or hear differently? No?
Do you have an example, like an example with data that uses sequential coding, or like a study that you could, so just to see like how it works in like with real stuff, real data?
In the very last slide that I added to this lecture, there's a reference to the textbook I stole the table from. In that textbook, there is an example using basically the same data set coded up a whole bunch of different ways, and they walk you through how the parameters change based on the coding scheme. That textbook is the textbook for the other class, and it is available at the library. You can get to it electronically. So I would recommend that. Odds are good we may have an example of this at some point in the semester as well. But the example that I have that follows is for this indicator coding version instead. All right. So here's an example then, a 4-group example to follow what you'd be doing in your homework. Let's say that I have a grouping variable that's looking at the effects of different types of treatment for whatever. I've got a control group that has the business as usual version, and I've got treatment 1, treatment 2, and treatment 3. Well, these are not really ordered. You could say that treatment should be higher than control, but you're not sure about the various treatment differences. So an indicator coding approach would look something like this, where if I want the control group to be my reference, which is a reasonable thing to do, they get a 0 throughout, and then D1 is going to represent the difference between control and treatment 1, D2 for treatment 2, and then D3 for treatment 3. So here's how the model then tells us what the model implied mean is for each of these groups. So right now, there's no other predictors in the model besides these 3 grouping variables. So these would be the actual group means as opposed to adjusted for any covariates. By the way, this slide is showing what? What is another name for this exact type of model? Anyone?
A linear model?
It's a linear model, sure. But if I
Is
have
it
just 4 groups.
ANCOVA?
Ah, ding! This is a one-way ANOVA, folks. That's what this is. So I point this out because other people will use the special names for different things, and so I want you to be able to talk to anybody to describe your model. So this is an ANOVA, a one-way ANOVA in this case. And so this table then shows how the model creates the mean for each group, where D1 is either 1 or 0, and it turns on to 1 if it's the treatment group mean. D2, same thing. D3, same thing. So what's missing then are these three means, because the model only gives us beta 0 directly, and the differences between the treatments. Do you think that those would be of interest? In a study that has 3 different treatment arms, might they want to know which one works relatively best? One would think, right? So here's the 3 differences that we already have. We know how control differs from each of the other groups because of the way we set up the coding. We've got beta 1, beta 2, and beta 3 that are going to pop out from the model. They have an estimate, they got a standard error, they got a significance test associated with them. The others are linear combinations. So the way that I built this is the one that's second minus the one that's first. So how 2 differs from 1, how 3 differs from 1, and then how 3 differs from 2. And so if the model tells us how to get the mean for each group, it also tells us how to get the mean differences. So you would have to ask it to provide a significance test, estimate, standard error, p-value, etc., for beta 2 minus beta 1. That is how the model tells you how those 2 treatment groups differ. Likewise, beta 3 minus 1, beta 3 minus 2. So that's one of the things that I found people don't always know how to do, and I want to make sure that you do. All right. Questions on that point? No? With me so far? Zoomers? Everybody's still here? Everybody's here?
Yeah.
Yeah, indeed. Excellent. So how can you do this in software? You got 2 choices. Choice number 1 is what I'm going to demonstrate and what I would ask you to do, which is set it up yourself. It's more work on the front end, absolutely, but there's a couple reasons why this is actually my preferred approach. One is transparency. Having to set up the predictor variables and code up the 0s or 1s then corresponds directly to the linear model representation of what you're doing. And you have complete control over what they represent. The alternative, once you get really good at number 1 and you're looking to save time, is to let the program do the coding for you. And so this is when you tell the program that you are working with a categorical variable. So it goes on the by statement of SPSS syntax, it goes on the class statement for SAS, it's an I dot variable instead of a C dot variable in Stata, and it's known as a factor variable in R. M+ does not have a way to do this, and that's the only program I know of that doesn't. The differences across programs, though, in terms of who is the default reference. So in SPSS and SAS, the default reference group is the highest group, either numerically or alphabetically, if it's a string variable. In Stata and R, the default is the lowest. So that's one thing to keep in mind if you're letting your program do your coding, is like, okay, what are they doing? This can be much more convenient if you have a lot of groups. So if you have a lot of groups, you have a lot of mean differences, a lot of means you got to worry about, you can tell the program that and it can produce this information for you much more efficiently. However, in the presence of interaction terms with categorical predictors, what it gives you is internally inconsistent. And that I have gotten many questions about, because literally in SAS output, you will see 2 different p-values for the same ostensible main effect of a group, because it's telling you 2 different things. It's either the marginal main effect averaging over the other variable that's part of the interaction, or it's a conditional main effect holding that variable that it's interacting with at 0. And those are not the same. So you can end up with confusion if you let the program do the coding as to what the heck you actually get back. And that's why I don't favor that approach until you're really, really good at doing the coding and you can figure it out after the fact if you have to. So this is what the program is doing under the hood when you designate a variable as a factor variable or a categorical predictor in whatever software. It is actually doing dummy coding predictors for you. And it does as many as you have distinct categories. It figures out how many categories you have, and it makes as many variables internally that it needs. So it looks like this. if you left these variables in the model as is, you wouldn't need intercept. Each of these variables is functionally a switch. So you would have predictor times control plus predictor times treatment 1 plus 2 and 3. You wouldn't need an intercept because it would be redundant. And indeed, this is the coding scheme that I sometimes go to for problems that defy standard coding. So a couple examples. Have you heard of SMART designs before? SMART designs are, I forget what it stands for, to be honest. It's an acronym that someone developed and ran with. But it's when you have an intervention design and part of the way through, you check to see if it's working for people, and if it's not working for some people, you re-randomize them to a different group. So it's an adaptive design designed to treat as many people as possible. But then you end up with this really weird nesting of control versus treatment splits, and then treatment splits to this and treatment splits to that. That kind of design defies standard ANOVA type models because you have holes, right? Because there's no analog of what the second random assignment was for the treatment group. So there's a whole literature on how to analyze that data. I say screw it and do this. I'm pointing at the SMART screen, and I'm pointing at the screen you guys are doing. Just create a separate dummy code for every possible mean and throw it in the model that way. You're laughing at me? Or are you jiggling? You
No,
look like-
I'm asking a question, but also laughing.
Yeah, okay, so there's some jiggling happening in the live audience that I'm not usually privy to because I only see your heads. So I'm trying to read the body language here. Yeah,
so
questions?
This is assumed. So when you set this up in like a program, you have to hold each category constant when you're, estimating parameters or like the coefficients. But what if you want everything to happen all at the same time and you don't want to hold other things constant? How would you? Would that ever happen, and how would you set that up?
I'm not sure I understand the question,
So, like, if you don't want to hold things constant, you want everything, like, if you had, like, 4 different categories, and instead of, like, estimating the coefficients one at a time, you wanted it all, I guess what I'm asking is that a multi-level effects model, or am I not?
So the question is, what if you don't want to control, you want to estimate everything at the same time?
Yeah, or is that even possible to do?
A multi-level effects, if you mean mixed effects, has to do with additional error terms. It doesn't have anything to do with fixed effects.
Okay.
The error terms build in sources of correlation among your units. That's what they're for. In this type of model, all 4 of those variables would have to go in at the same time for them to mean what you think it means.
Okay.
So for instance, if I screwed this up and I just put in control by itself, then what I have is lumping all of these 3 treatments together versus control. And that may not be what I want it to be. So they all go in together. But in designs where you have a bunch of groups and they're not perfectly balanced, like in the SMART designs or in designs where, let's say they forgot to catch a control group. I've seen that happen before too, where they have like cohort 1 has control versus treatment, and cohort 2 has control versus treatment, and then in cohort 3 something went wrong and they only ended up with the treatment arm. Well, then you have ANOVA with a hole in it, right? You're missing one of the cells. So in that kind of design, you may end up with something like this, where you just have a separate variable for each group, and then after the fact, you can ask for whatever comparisons of the group that you want to. So that's what I would do in that case. But this is what it's doing for you under the hood when you make a variable categorical. So then it figures out, if you have the intercept in the model, how many of these it actually needs. And if you look at SAS proc GLM, it gives you error messages that your matrix is singular and it fixed it for you. What it's saying is that, yeah, I figured out that you don't need all of these if you have an intercept, and I left one out for you. You're welcome. The question is which one that it leaves out. So in SAS, for instance, it would leave out treat 3 as a variable, and then look what's left. Treatment 3 becomes the reference because it's zeroed out everywhere. R and Stata would leave out the first one, and look, control becomes the reference because that's where it's zeroed out. So every time you refer to this type of variable, like which would be called, say, just group, like I.group or factor group, internally, it wants to know what it's supposed to do with all of these 4 variables. So you end up having to write like 0010 or -1100. You have to address what it's supposed to do with each of these coding variables. So the syntax looks different in that case because you have to tell it what to do with these. Okay. Anywho, yeah, I have another example. Questions? Comments? All right. Here's another one. What about a semi-continuous predictor? Here's something that you may not have seen, but I think more people should know about, and I guarantee this is going to be in one of your homeworks. I guarantee it. I'm not telling you which one, but one of them. So this type of coding scheme is useful if you have a variable that is both kinds of people and amounts. So for instance, if you have something like amount of sexual abuse that you've experienced. Now that's not good, right? Ideally we'd want everybody to be on a 0, but unfortunately some people are not 0. But if you gave a questionnaire about sexual abuse to, say, an undergraduate psychology pool, hopefully most of the people there would not have any negative experiences and they would be on 0s. So if you want to treat that variable as a kind, like who has a history of sexual abuse versus who doesn't, that's one kind of variable. But if you wanted to treat it as how severe of a history of sexual abuse do you have, that's a different variable. And so the right way to characterize both of those things simultaneously is to literally represent them as different variables. So we have things like abuse or other kinds of behaviors that are not common, where you would see a lot of 0s. If you have a sample of people who smoke and people who don't smoke, and you ask them something like, how many cigarettes do you smoke in a given week? You're going to have a bunch of people who say 0. Regardless of which week it is. So you can make a variable that is whether or not you're a smoker, basically. Like, do you smoke at all? You're a smoker, if so. And then how much? So within the smokers, only would this second variable logically apply. It's a nested effect within the smokers, the way that it's coded. And you would create it such that one cigarette or one experience, however you want to think about it, is the reference point for amount. So if you put these together, then you can describe kinds of people and severity within the people for whom it's relevant as an experience. So it's putting both together. This is also known as piecewise slopes or linear splines, because essentially what you're doing is allowing one slope for the difference between 0 and 1, and another slope for the remaining differences after 1. So 2 slopes in the model is what this looks like. And here's the code to do something like this. So you would have to have separate statements for whether or not someone has a 0 or something else, and then recode the variables based on their pattern. So I wrote it for SAS in Stata. I was going to look it up for R. Note that this one right here is one statement. It's the longest one here. I had to fix it. And Jonathan helped me figure that out. So giving him a shout out. He walked into my office and I was like, how do I do this in R? And he just started talking and I just transcribed what he said. So thank you. I'm still working my way through R. So just want to give you a taste of sort of different coding schemes and how to represent things. When this type of variable is a predictor, this is how I would think about it. You would create a type and amount as separate variables. But if it's an outcome, that's where we get into the family of zero inflated count models. And you can either represent this type of coding scheme via what's called a hurdle model, we'll get to those later, or a zero inflated model, which is less intuitive but more common. All right. It's hot under here. Do any of you have to lecture in a mask? Yes, can I get an amen? It's hot under here.
Yeah.
Amen. Yes. Well, thank you for all wearing your masks as well. Wow. Okay. What's next? There we go. What does linear model mean is one thing that I want to clarify. Linear model doesn't mean that we can only have linear effects. The difference between this is whether a model is nonlinear in the variables or nonlinear in the parameters. If, for instance, I want to have a quadratic effect of a quantitative predictor, so a U-shaped function where you're actually higher or lower in the middle than you are on the ends, I can do that, and it's still a linear model. We would say that that model is nonlinear in the variables, because in order to fit a quadratic effect, you'd have to have a predictor squared as one of the predictors in the model. But it's not a nonlinear model. A truly nonlinear model would look like this, something like this. This is an exponential model, for instance, e to the. So it's a nonlinear function. This kind of model does not work in standard linear model software. You would need something special. So like NL mixed in SAS, I think there's an analogous program in Stata, and I'm sure there's many of them in R. So we're staying in the world of linear models that are nonlinear in the variables. We're not heading into this world in terms of the linear models. Then the question is, how many slopes do we need to characterize each effect? So if I have a binary predictor or a quantitative predictor whose effect is linear, that only takes one slope. If I want to capture a nonlinear trend of a quantitative predictor, such as a kind of person and severity, like we just talked about, or a piecewise model of any other kind, then I might need two slopes to capture a nonlinear effect or a quadratic effect. If I have C categories, I need C minus 1 slopes. So there are lots of instances in which to fully describe the effect of what is conceptually one variable, like number of cigarettes is one idea, but it took two slopes to represent it. Or we have ordinal happiness as one idea, but it took 4 slopes to represent it. Or age, for instance, is one idea, but I need a linear age and a quadratic age. There's all kinds of instances like that. One thing that you want to know how to ask for is a joint hypothesis test of all the parts of the predictors that together create the total effect of that predictor. So that's another thing that I want to make sure that you know how to do before we head into generalized models, because there are not as many things that pop out by default in your software as they do for linear models. So multiple fixed effects at once can be requested in any program. SAS contrast, Stata test. In R, there's different ones. There's GLHT for linear models. There's contest MD for multi-level models, and I'm sure there's others. In M+, it's model test to do this. Special cases of this idea of when you need to lump together multiple fixed slopes to test an idea. Special cases of this you've seen. The first thing that you would have seen is the model F test for the R square. Think about it. If I have 5 predictors in a model, I get the significance and effect uniquely of each predictor in a table, right? But I also get like the ANOVA summary table, as it's called. I get an F test for whether the amount of variation that's accounted for by my model per predictor is more than what the variation is left over per predictor I could have added. That idea. So you're lumping together all the predictors in the model to get one F test, and that F test tells you whether your model R square is significantly greater than 0. In linear models, you don't have to ask for this. In generalized linear models, you do. So I want to show you how to get it. So F in general is going to tell us, weighted per slope, what is the contribution of these slopes? So the danger that you risk in combining things is always, what if you have one slope that's really useful and the other slope sucks? Then the F test for their joint contribution is going to be like down-weighted by the one that sucks. So that's one thing to keep in mind where this can potentially go awry, but there's a lot of different hypotheses that lend themselves to this. So not just the R square. Have you heard of an omnibus F test? Design of experiments, analysis of variance, that whole field? The phrase omnibus? What that means is that you are lumping together all of the different fixed slopes that it took to fully describe all the mean differences of your categorical predictor. That's a special case of this. if you run a what's known as a hierarchical regression model, where I put in like my covariates, and then in another block I put in 3 more things that I care about, and I want to know if those 3 more things significantly increased my R-square, that's this too. So these multivariate F tests are used anytime you want to lump slopes together. There's a lot of times when that is necessary. When it takes more than one slope for a predictor, when you want to test the R-square, or when you want to test an increment to the R-square across multiple slopes. And by the way, what you end up with across programs is going to depend on the program and whether you end up with using denominator degrees of freedom. If you try to do this lumped together hypothesis test in a program that doesn't use denominator degrees of freedom, like in Stata for some of the generalized models, you'll get a chi-square instead of an F. But F times the number of slopes is chi-square. So there's a 1-to-1 correspondence in the test statistic. There will be a difference in the p-value though, because chi-square doesn't use denominator degrees of freedom, whereas F does. So I want to be ready for that. And the same thing is true for single slope hypothesis tests. If you're only testing one slope, the t-value that shows up if you square it is the same thing as F. If you're testing one slope without denominator degrees of freedom, you get a z instead of a t, and if you square that z, it's chi-square. So those are the only 4 kinds of test statistics that we're ever going to work with, pretty much. Okay, let me back up a second. There. Questions? Comments? With me so far?
I have a question.
Yes, please.
Is multivariate word test is F test? As you think?
The question is a multivariate wald test an F test? Depends on who you ask. Technically speaking, a wald test is a z test of a parameter. But if you think of it as a modified wald test, if you add degrees of freedom, then it turns into t. Likewise, a multivariate wald test traditionally is chi-square. But if you want to use denominator degrees of freedom, then it turns into an F. So I've been yelled at by people about this before. You can't call it a wald test. I just did. The key idea is, are you testing one thing? That's T or Z. Are you testing more than one thing at the same time? That's chi-square or F. And there's a lot of cases where you need to test more than one thing at a time, and it doesn't necessarily just pop out in your output in certain models.
Do we ever want to not use degrees of freedom?
Do we not ever use degrees of freedom?
I mean, is there a situation where we wouldn't want degrees of freedom? Because when we do, we get like get different test statistics, like F instead of chi-square.
So question was, is there ever a situation when we wouldn't want to use denominator degrees of freedom?
Because I know we have something called the chi-square test and stuff like that, but
Yeah, the chi-square, sort of the crosstabs thing,
Yeah.
is a normal approximation, but the sample size is built into the table in a way that I think makes it a little bit different. At asymptotically, enough denominator degrees of freedom gets you to the same critical values. So I would say that it's probably in your best interest to try to use denominator degrees of freedom if possible, but that will not be possible in certain combinations of software and generalized linear models. It is possible in some, it's not possible in all of them. So, all right, let me see, where are we at here? Okay, interaction terms. That's where we got to get to so you can do your first quiz. Come on, there we go. So taxonomy of words that you will hear come out of my face. So I want to introduce them to you when I say them. So all fixed effects in a given model are either an intercept of some kind or a slope of some kind. The rest of this pertains to slopes. We can think about slopes in terms of how they are interpreted as falling into 3 categories. So a slope is always the same definition. It's the difference in y for a 1-unit difference in x. But the context of what you do with that number in terms of how it addresses research questions and what it means specifically in regard to the other predictors in your model. That's what I'm talking about. So all slopes are either going to be bivariate marginal, unique marginal, or unique conditional. So what's the difference? If you only have one predictor in your model, then it can only have a bivariate marginal slope. So bivariate meaning the full relationship between that x and that y, not controlling for anything else. So like the same thing as Pearson correlation, just a sort of two at a time relationship. And because there's no other predictors, that slope is marginal. That slope applies to everybody regardless of the rest of their data. So I would say, for instance, if the slope is 2, that 2 holds for everybody. And 2 reflects the full relationship between x and y. If you have a model with more than one slope, which is going to be most of the time, then the language that I use for that idea is unique. The slope is the contribution of that predictor uniquely to the model after controlling for, after adjusting for, after taking into account, whatever you want to call it, the other predictors. So any covariance that the predictors share does contribute to the model outer square, but each predictor individually does not get credit for their shared contribution. It only gets credit for what it uniquely brings to the table. So your unique effect is a predictor effect after controlling for the other predictors. Then we get to the tricky part. If a predictor is not part of an interaction term, its effect is marginal. It holds for everybody. So I can say the effect of x on y is 2 after controlling for z, but that 2 is for everybody. If a predictor is part of an interaction term, then its unique effect is conditional, meaning not only are you controlling for z, but if x and z interact, the effect of x is specifically when z is 0, not just controlling for, but controlling for and holding at a specific constant. And the same is true for the effect of z. And this idea that those effects are not only unique, but conditional on the 0 value of any predictor that interacts with them, those are what the literature tends to call simple slopes, or otherwise known as simple main effects in ANOVA language. Now I bring this term up because I guarantee you will have seen it at some point, but I also want to point out my annoyance with calling anything simple. Like, why piss off your readers by telling them that this is easy? Likewise, if you're ever writing a document, don't say things like obviously or clearly or it is evident from equation 3. Simple slopes to me like brings that up, but what they mean by simple is conditional, specific to. And so that's the middle 2 questions of your quiz that I was hoping to get through today. For example, if I have a model like this, so I'm just throwing letters in here. We'll have an actual example with real variables and numbers. This is just sort of a generic idea to get us started.
That's the time I'm waiting for.
Say that again?
That's the time I'm waiting for.
That's the time you're waiting for? Okay. So let me give you the big picture idea, and then we'll give you a specific instance, and then you get to practice it in your homework.
Right. Thanks.
Yep, that's what we're going to do. I have found in the past that when I went straight to an example, folks over-regularized, like it didn't think it applied outside that example. So that's why I'm trying to talk about it kind of generically first, and then have an example, and then you get to practice. So that's my method anyway.
Right.
All right, so this equation right here, W as a predictor all by itself. Beta 1 slope then is bivariate marginal. It reflects the full relationship between W and Y, uncontrolled for anything else. And that slope, beta 1, holds for everybody. Cool. This, by the way, would be called simple linear regression. Again, pissing people off by using demeaning terms. If it were a quantitative predictor, this would also be called a 2-sample t-test if it were a binary predictor. Whatever. Now I have a model that's more complicated. So I would call this a main effects only model, because each of the predictors is not part of an interaction term. So I've got the slope for W, the slope for X, the slope for Z. So these switch from bivariate to unique because each of these slopes is controlling for the other predictors in the model, but each of the slopes is still marginal. So beta 1 is the slope per unit W for everybody. So if I have a hypothesis test about W, to answer a research question as to W matters, does W matter in predicting this outcome? If the hypothesis test says yes, then I say yes, it matters. And if the hypothesis test says no, I say no, it doesn't matter. The end. Now this model, W is still here without an interaction term, but I've picked up an interaction term between X and Z. So it is still the case that beta 1 is unique marginal, because it's still controlling for X and Z, and W is the effect for everybody. Beta 1 is the effect for everybody. The other two switch. So beta 2 becomes unique conditional, because not only is it controlling for W, it is specific to when Z is 0. That is what it means. So if I get a hypothesis test about the effect of X, and it has a significantly positive slope, I can't say X matters, it helps things. It helps things if Z is 0, but I gotta stay tuned for what the interaction is gonna do to it, because the interaction could amplify that slope as a function of Z, or it could diminish it as a function of Z. So I don't have the whole story yet with respect to X. The one that the model gives me is just one of an infinite set of possibilities, a different one for each value of Z. And that's yet another thing I want you to learn how to ask for. Likewise, beta 3. The reverse, same situation. If I have a significant effect of beta 3 in my model, I can't say unequivocally that Z matters, because that is the effect of Z when X is 0. I don't know what it is for anybody else yet. So these are the types of models in which deciding ahead of time how your variables are centered matters. Because 0 is what these fixed effects are representing for the interacting variable. If 0 is outside the scale of your data, then beta 2 and beta 3 are garbage. Beta 4 is the interaction term. Now I would call this unique marginal. It's controlling for W, and there is no higher order term that includes both X and Z, so it's marginal, meaning beta 4 is the interaction term for everybody. But what do I do with it? That's the question. So where folks go wrong in trying to interpret interaction terms is trying to talk about what an interaction term does to a predicted outcome. That is incorrect. Instead, talk about what an interaction term does to each of the slopes of its interacting variables, and then what the slopes do is adjust the predicted outcome. So think of like a two-level structure here, where the interaction term has its effect on the main effects then affect Y. The good news is that there's only 4 possible kinds of interaction terms in the entire world. And so I'll show you those in just a moment. Either way of an interaction is correct. So we can talk about beta 4 as how the slope of X is moderated by Z, or I can talk about it as how the slope of Z is moderated by X. In practice, the way that a question is phrased will guide you to which way to go. Almost always you'll have a research question where the moderator is made explicit. Does this effect hold for this kind of person and that kind of person? Does this effect increase for people like this? So real life research questions that use these phrases are things like buffer. Is the effect of stress on illness buffered in people who have better coping strategies? Is the effect of low SES on children's achievement buffered by sending them to Head Start preschool? That kind of thing. So that buffer type hypothesis is to take a negative effect and make it less negative, less harmful. The other way would be like a risk factor. So is the relationship between stress and illness exacerbated in people who have less money? Yes, the answer is yes, I can tell you that. Because not having money is stressful, and you have shitty health care if you don't have money too. So does a variable make something worse or make something better? Those are moderation hypotheses. So we can figure out for any person what the model implied effect of x and z would be in this model. And here's how we do it. And this is what I'm asking you to practice in your first formative assessment, question 3. So if I want to know what the model says the effect of x is for anybody, here's how I do it. Go up to the model, find all the terms that have x in them, bring them down. I got a beta 2 times x, and I got a beta 4 times x and z. Take x and factor it out. Stick it in the back. What's left is how the model says the slope of x should be constructed. So this term in brackets is the slope of x according to the model. And this term in brackets illustrates why we interpret beta 2 as the simple effect of x when z is 0, because that's the only situation in which this second part with beta 4 drops out, and the slope is just beta 2 all by itself. So the beta 2 that you get out of the model directly is when z is 0, but you can ask for any other x slope at any level of z as a linear combination with these additional statements in your code. Okay. How are we doing?
Good.
Fine.
Good?
Mhm.
Okay. Z, same thing, but backwards. To figure out what the model says the slope of z should be, up to the equation. Find all the things that have z in them. Factor out z, there's your linear combination. So you can do this in any program. And this is one of those things that I did not learn until I was on the tenure track, okay? I want to give this to you way sooner. Because you know how I was taught to do this? Recenter your variables and rerun the model. Yes, people are shaking their heads, that is correct. No. I once taught a workshop on multi-level models where I demonstrated this because interaction terms are always in multi-level models. And I had someone come up to me at the break and say, oh my God, I wish I had known this last week. I just ran 90 different models to get the slope at every possible level. Oh my God, no. Now that would be a lot of statements, although I can figure out a way in my head to loop as necessary, and Stata has really nice features for looping through this in their lincom/margins commands. But yeah, I was taught the hard way, which is to re-estimate the model, changing where 0 is, and that gets very confusing very quickly, so we're not doing that. Yes, you from the audience, correct. You or head shake and discuss. I would also accept facepalm as that. All right, so yeah, we're going to do a lot of interaction terms. 4 kinds. Interaction terms are not hard. I'm telling you that right now. Much is made about how to test moderation, and people write special macros and programs and R packages. It's not hard. There's only 4 kinds. If you have a main effect slope, that slope is either positive or negative. The interaction term either makes it more or less the direction that it was already headed. So if you have an interaction term that makes a main effect slope more positive or more negative, that's known as an over-additive interaction. It's an amplification of the slope at higher levels of the interacting predictor. If you have an interaction term whose sign is opposite, so it takes a positive slope and makes it less positive, or a negative slope and makes it less negative, that is a dampening or diminishing of an effect. So it looks like this if you put it together with the model that we had. Let's say that the slope of x is 10. So beta 2 is 10. if I fit a model and I get an interaction term for beta 4 that's 2, the way that I talk about that 2 is beta 2 is 10 when z is 0. For every unit higher z, that beta 2 slope is more positive by 2. Stronger. If the slope for beta 2 for the effect of x from the model is 10 and the interaction is negative 2, then I would say for every unit higher z, that slope of 10 becomes less positive by 2. Meaning if z goes from 0 to 1, the slope is 8. Then it goes to 6. Then it goes to 4. Likewise, if I start with a negative slope and I've got a negative interaction term, that negative slope is made more negative as z goes up, stronger. Negative slope made less negative as z goes up is the last one here. And at this point, people are usually like, yeah, I can't write more positive in a results section. People aren't going to know what that means. And that's where you get out your GRE words, right? Words like exacerbates, amplifies, enhances, right? There's a lot of ways you can say more positive in English, fancy English even. I once had someone argue with me that less positive and more negative were actually the same, like heading in the right number line. So if you start here and you're going to less positive to 0, you end up at more negative. They're not wrong. But I will tell you that there is a difference between saying something is less good for you or bad for you, right? That's not the same thing.
Yeah, I mean, in terms of direction, they're the same, but if you take positive to mean the thing was already positive and it's getting less positive, that gives you more context.
Yeah, if it's already positive and it's less positive, then that is the context. So I will tell you that the weather talks about it this way. If you look at the words that is written on your weather forecast, on the Weather Channel or on whatever app, it says things like not as cold. It does not say warmer because we're all the way up to 30 degrees today. It says not as cold. Or alternatively, if it's been 90 and now it's going to be 80 the next day, not as hot. Still hot though, not as hot. So to me, these are 4 different things. And I want you to know how to take it apart for any kind of model. So the example that I have in your first formative assessment then is a model that looks like this. It might even be this model for what I know. I'm not very creative. I use different letters, but it's kind of the same. So what if I have 2 interaction terms? Well, beta 1 then is interacting with only z. So beta 1 is specific to z equals 0 only. X is interacting with only z, so it's also specific to z equals 0. But z is interacting with both x and w, so it is conditional on both. So the resulting linear combinations that you would need, then you would have to have both when you're talking about beta 3. So here's the math on slide 21 that it works out. W is the same type of linear combination. Go up to the model, find all the things that have W, factor it out, here's what's left. X, there's only 2 terms that have X, factor it out, here's what's left. For Z though, I've got 3 terms that have Z in them, so when I factor that out, I've got 3 terms that are left. So I cannot talk about what the effect of Z is without saying who it's for with respect to X and with respect to W. I can't. And that's where people get into trouble if you don't know this, which is why I'm making it such a point, and I start off almost all my classes with a version of this lecture, is because I see people doing things like, oh, well, you know, beta 3 is not significant, so Z doesn't matter. You don't know that. It doesn't matter for X equals 0 and W equals 0, but who is that even? Did you center your variables? Does X equal 0 even exist in your data? So just interpreting the stuff that is given to you is going to be insufficient for models that have moderation interaction terms.
Oh, so centering would also affect the significance of interaction terms?
Centering will not affect the significance of the interaction term. It will affect the significance and the parameter estimate of the variables that are part of the interaction term for their main effects.
Oh, okay.
So beta 1 depends on where z is.
Yep.
Beta 2 depends on where z is. Beta 3 depends on where x and w are. So what you get is how you set it up.
Okay.
So one thing that I don't have a lot of time to talk about, but I wanted to point out is this regions of significance thing. There is an article I did add to your list that talks about this idea. And it's trying to describe the range over x and w for which z matters. That's the basic idea. So if it doesn't matter at 0, it doesn't matter at 1, doesn't matter at 2, and it finds the boundaries where the effect either turns on, is negative, and in one direction, becomes non-significant in 0, and then turns on in the other direction. And there's an R package that does this. I have an Excel spreadsheet I made that does this, and I wrote a SAS program that does this. So in my example, I'll show you a little bit of that. But it's 1:46, which means I gotta stop talking. Any questions before we adjourn for the day? It's a lot, I know, but we will have examples to follow. All right, then I will let everybody go for today. Thank you for joining me either in person or the Zoomers. I appreciate your attention. I hope this format worked okay. Let me know if there's anything that I can do differently or better to improve. Otherwise, I shall see you on Tuesday. Have great weekends. Stay safe. Goodbye, everybody.